Okay, now that we talked about the concept behind nested cross-validation, let's take a look at a code example. So this will help you kind of to understand nested cross-validation from a computational perspective, but I also hope that will be useful for your class projects when you are comparing algorithms in your class projects. So the code examples are available on GitHub. So I uploaded them to our regular class repository under L11 code. And in fact, there are actually 3 notebooks. So there is one I called verbose 1, there's one I called verbose 2, and a compact one. All of them produced exactly the same results. It's just like the implementation or the way I got there is a little bit different. So in particular, I implemented the outer loops a little bit differently. So the verbose one is the more manual way, using stratified k-fold manually. Verbose 2 I was using the cross-validate function, and in the compact way I was using cross-val score. So they all give different levels of information when you look at them. So I think the verbose 1 is the maybe easiest one to read for now, because you are already familiar with the stratified k-fold object. And to be honest, it doesn't really matter which one you use. Actually, I would probably not recommend the compact one, because it provides less information about the hyperparameter sets. I can just briefly show you how they look like after we talked about this notebook here though. So let's take a look at this notebook here now, where we have the manual approach. So here's again an illustration of nested cross-validation, how it looks like. So we have the outer loop, which we use to run the inner loops. So for each outer loop, we split the folds into a training portion and a test portion, and the training portion is then passed to the inner loop, which carries out hyperparameter tuning or model selection. For that, we can, for example, use grid search, like we learned about in last week's lecture. So here that's just setup stuff. So watermark just to see what versions we are using. Then here we are importing a lot of things. So most of them are familiar to you. Grid search for the model tuning in the inner loop, just splitting the data set, stratified k-fold, cross-val score. I don't think I'm using it in this notebook, but in the other ones. Pipeline, standard scalars, and then classifiers we want to compare, and the MNIST dataset. So here we are using a smaller version of the MNIST dataset. It only has 5,000 training examples, just to keep it computationally also feasible. This notebook already took like 20 minutes to run on my computer, so it's quite expensive. So I'm splitting off 20% as test data here also, so that we can compare the nested cross-validation performance to the test set performance. They should be very close to each other. Okay, so now we are initializing the classifiers first. We are using a logistic regression classifier, in particular a multinomial logistic regression classifier. In deep learning, this is also called softmax regression. We're just doing that. I know we haven't covered it in this class. We will cover it in statistics 453. The reason I'm using that here is so that we have more algorithms to compare, and this one is relatively fast to run compared to the other ones. And the support vector machine here is also relatively fast, at least the linear one. It's just so that we have a larger variety of algorithms to compare. I was also considering including adder boost and gradient boosting, but it would just take a little bit too long here in this notebook to run all of them. Because I wanted to get the lecture here out and didn't wait too long, because I also had to run this 3 times. Okay, so these are our classifiers we are going to use, and note that for decision tree based classifiers, like the decision tree itself and the random forest classifier, we don't need to scale the parameters. Parameter scaling doesn't really matter for them. So we only do the scaling of the parameters for the other classifiers. So in order to facilitate that, we use the pipeline, where we combine the standard scalar with the classifier itself. So for the logistic regression, k-nearest neighbor classifier and support vector machine here. So you can also then think of our pipeline as the classifier. So the classifier consists of 2 steps then, the scaling and the regular classifier then. So for each classifier, we consider a hyperparameter grid that we want to search. So these are the parameters we consider tuning. For logistic regression, we consider regularization weight penalty. So we consider only L2 here. And then different regularization strengths, so how much the weight is penalized. You don't have to really know what that means here for this class, it's just so that we have some parameters to tune. For nearest neighbors, we consider the number of nearest neighbors and then also the distance. So if we have the Minkowski distance, P1 would be Manhattan distance and 2 the Euclidean distance. For the decision tree, we search over the depth, the maximum depth, so a value between 1 and 10, and then also no depth, so none. And the criteria for information gain, Gini or entropy. For the support vector machine, here it's a little bit more complicated because there are actually 2 support vector machine algorithms we are considering. One is the RBF kernel machine, that's a nonlinear kernel support vector machine, and this is a linear kernel support vector machine. And only the nonlinear one supports the gamma parameter. So here, this is why I'm having 2 separate dictionaries, because if I would use the gamma for this case, there would be an error. And here C is similar to the C here, it's like the regularization strength. And for the random forest, we are searching over the number of estimators. If you recall from the model ensemble lectures, I mentioned that usually it's better to run random forests with as many estimators as you can. So this is usually generally true as a rule of thumb, the more estimators the better. So in this case, it's maybe not making sense to search over these, but you can think of it in practical terms that maybe you can get away with a smaller number if you find, for example, that the smaller number performs equally well as the larger number. The tie breaking in scikit-learn is usually sequentially, so it would select the smaller one if there's a tie in the accuracy, and using a smaller number of trees may be good if you want to save then computational performance. So if you think back of the program, this archive sanity preserver, if you find that the random forest performs best and 100 estimators gives you the same performance as the 10,000, then why not going with 100, because it will be much more efficient on the machine, on the server that you're running, because you need fewer trees per random forest. Okay, so now we are first setting up the inner loop. So we are right now, if I scroll up, we are right now here setting up the inner loops. We're just setting up the inner loop, we're not running it. And then later when we set up the outer loop, we are providing it with the information how to run the inner loop and then also execute the inner loop. So now let's then set up the inner loops. So for that we use the stratified k-fold class. So this is we are doing 5 times C nested cross-validation. So we have 5 outer folds and 2 inner folds. So this is why we set the number of splits to 2, because we're now looking at the inner fold. And we are also setting up a dictionary for our grid search objects. So here we are doing grid search, not randomized search. You can also do randomized search, but it's more common to use grid search in nested cross-validation. So, and then what we are doing now is we are just iterating over our combinations of parameter grids with a classifier and then its name. So the name is just so that we can save it in the dictionary and assign a name so that we can find it later. So we are iterating it, and for each classifier here, we are creating a grid search object from the grid search CV class. So we are giving it the estimator. The estimator is the second object, so it's like in the first iteration pipe 1. So it gets, let's say, pipe 1 in the first iteration, then the corresponding parameter grid, and it uses a stratified k-fold, so the 2 splits from stratified k-fold, and by default what it will do, it's set to refit to true. So what it will do, if I go back to the image one more time, it will carry out the k-fold cross-validation with grid search. So it will run this part, find the best hyperparameter by running this on the different hyperparameter settings. When it's finished, it will find the best hyperparameter settings, so that's based on the average accuracy over these validation folds. Then it will take this setting, if refit is set to true, which it is, and fit a model with this setting to this whole training fold. And then we can use that fitted model on this training fold with the best settings to estimate its performance on this test fold. Okay. So yeah, and now it's a little bit complicated. So I think also if you, after this video, maybe step through this by yourself, line by line, and look at it, I think it's also maybe easier to understand. It sometimes takes a few looks to understand some concept like that, because there are many things going on here. But I will try my best to explain this here. So we are initializing these grid search objects, and then right now these are essentially how the inner fold is run, but we're not running it yet. We are just saving it in this dictionary here with the name corresponding to it. So in the first iteration, this would be pipe 1, this would be param grid 1, and the name would be softmax, and then we are just saving it here. Next, we define the outer loop, and the training folds from the outer loop will be used in the inner loop for model tuning. So that means that here this training fold will be used for the model tuning in the inner one. Oops, yep, that happened to me before. I don't know if I accidentally drag it, what it does here. Okay. So what I was saying is the training folds from the outer loop will be used for the inner loop that we just defined here. And the inner loop selects the best hyperparameter setting, and the hyperparameter setting can then be evaluated on the test folds. That's what I explained earlier when I showed you the image. So here is the outer fold. So what's going on? We are iterating over our grid search objects because we are using them in the outer fold in each round. So I'm doing that also just to print the name of it, and then later we can also estimate its performance then. So it's just for logging purposes here. So we are collecting the outer scores. So this is for each algorithm, right? So we are running nested cross-validation for each outer loop. So for each algorithm, one iteration for each algorithm. So we are just running nested cross-validation 5 times because we have 5 algorithms. So, and for each algorithm, we collect the scores on the test folds. We use stratified k-fold for the outer folds. So this is 5 times 2 cross-validation or nested cross-validation, so which is why we set n splits to 5. And then we split this outer CV here into training and validation indices. So I call this a valid index for validation index, but this is essentially the test fold here. Okay, and then here is where I'm using my inner folds. So run inner fold hyperparam tuning. So the inner loop, not inner fold. The inner loop hyperparameter tuning. So what's going on here is we are fitting the grid search objects. So these are the grid search objects that I defined earlier here. So for example, for pipe 1, softmax parameter grid 1, we would run this here, fit the grid search on the training fold of the outer loop. And then because refit is true, it will be then also be refit, the best hyperparameter setting will be refit on this training fold. Like you learned last week, after running grid search, there will be the best score and the best params that we can take a look at. So here we are just printing this out so we can take a look at it. And here we are computing the performance on test fold, on the what I called valid index here. So this would be the this would be the test fold. So this will give us the accuracy. And then we are this is after the for loop. So this is after doing the outer loops. We average the performances of the outer loops. So here, if I go up one more time, so here we are averaging over the performances of the test folds here. And this is what we then can use to select the best algorithm. So now this takes like 20-30 minutes to run. So I ran this beforehand. Now let's take a look at the results after running this. So the first algorithm, I think it's alphabetically, because dictionaries in Python are now alphabetically sorted. So the first one is the decision tree here. So what we can see is, the performances are quite stable over the outer folds. So, this is the average of the inner folds. The outer folds is here. So we can see 75% on the first outer fold, 78 on the second, 77, 74, 77. This is for the diagonals that I showed you for these here. And then the averaged performance over these test folds would be 76.75%. Also, I was printing the best parameter settings for each of those decision trees, for each outer fold round. And you can see, yeah, they are somewhat consistent, but they're not quite. There are 2 8s, 1 9, 1 7, and 1 none. Looking at the one with the best performance, this would be the one with 7. So this would be our best case. But of course, we don't know whether it's really because the model performs better, whether it just happens to be a better training set, whether the test set or test fold is easier in this case. So just looking at this, if I would consider something to choose in a real scenario, might be this one. But we can also, on the whole training set after we selected our algorithm, just run k-fold cross-validation again to find a good parameter on the whole training set. I will talk about this briefly after we looked at these algorithms. Okay, so this was the decision tree. Next, k nearest neighbors. So, here the performance looks already a little bit better. So if 91, 91, 90, 90, 90, so this performs a little bit better. We see Manhattan distance is here recommended. Could be that it's just tying with the Euclidean distance, that there's no difference, and tie breaking and scikit-learn is usually choosing a smaller one. Interestingly, 1 nearest neighbors is performing best in all cases, so that's unambiguous. Okay. Random forests. So what do we have here? So here we get better performances. So we get actually 95%, 94, 94, 92, 93 on average. Yeah, almost 94% accuracy. In all cases, or in 3 out of 5 cases, more estimators is better. It could be that this is tied with 10,000 in this particular inner loop. We don't know. Could have printed more information about the inner loops. But in that case, random forest. We already know random forests perform better than these other 2 algorithms. Then we have the support vector machine. In 3 out of 5 cases, the linear one is better. In 2 cases, the RBF, the nonlinear one, is better. 91.8, slower than our random forest. And then softmax, it had some convergence issues here. Still did somewhat fine. So we get 19. So yeah, it's almost the same as the support vector machine, a little bit lower. Okay, so now looking at this, we can say that the random forest performs best, right? So we find that the random forest performed best. So what we can then do is, in this case it's trivial. We could just say we pick the number of the highest number of estimators, or we can pick the one that has the highest accuracy on the outer test fold. We can say 1000. Let's say this would be a more complicated algorithm with other settings. One way also to find a good way to select a good setting for this, for the model, would be just to run k-fold cross-validation. Now, so after we selected the model, now say we selected random forest, we can run k-fold cross-validation on this whole data set here, on the original data set, with the regular procedure we talked about last lecture, like grid search, and then find the best model, set refit to true, and then evaluate that model on the test set. So we have then one single model that we can use in an application, for example, if we wanted to. In some applications, like I mentioned in this archive sanity preserver, we maybe don't need a fitted model because the model will be fit to the user. However, if we want to have a model, we can then actually do that. We can find the best hyperparameter setting on this original data set and then evaluate this on the test set. So this is what I was doing here. Where are we? That was what I was doing here. So here I was just picking the best classifier. So this was the random forest. CLF5 was the random forest. It was not the 5th in the list here earlier because the dictionary got sorted. But if we go back to the top, this is our random forest here. So going back down, sorry for scrolling so much. So here now we are then running a regular grid search, regular k-fold cross-validation. Actually, I'm only using 2-fold cross-validation. Could have used 5-fold cross-validation to fit the model or do the hyperparameter tuning on the whole data set. In this case, it finds the 10,000 modeled estimators decision trees is best for the random forest. And refit is true, so the model is fit to the whole training set, and then we can evaluate it on our test set. So that's what I'm doing here. So this is not necessary. We don't need to fit it on the whole training set because it's already done with refit equals true. And we find that the test accuracy on the independent test set is 94%. And what's kind of nice is it's also consistent with the performance we got in the nested cross-validation. So in the nested cross-validation, we got 93.98% on average, averaging over the outer folds, which is kind of the same as the test accuracy, almost exactly the same. So yeah, the nested cross-validation procedure in here, in this case, was pretty good. It gave us the performance that we would get on the test set without actually using a test set, right? So here, that's the 93.8%. So yeah, this is it for this notebook. That was the verbose 1 notebook. This one is the verbose 2 notebook. I mean, it's not super interesting. I was just replacing the way I did the outer fold using this cross-validate function, which is a, I think, relatively new function in scikit-learn. It came out like 1-2 years ago. Broader. So yeah, here I'm just using cross-validate instead of what I was doing here was using my stratified k-fold manually. I mean, it really depends what you prefer. So I find actually, this is the same thing. So I don't find any advantage of doing that over the other. That really is up to you. Yeah, one advantage is that you can set the n jobs to -1 here. That's maybe a good example to highlight. But if you do that, you can't set n jobs -1 here, just to keep that in mind. So maybe this is actually better because you can set n jobs to -1, which you can't trivially do here. So that's one advantage. However, you can set the n jobs -1 in the random forest here. So that's what you can do. You can set to speed that up, set n jobs -1 here. One thing you have to be careful though in scikit-learn is you can't have multiple n jobs -1, because now imagine I have n jobs -1 here. It's using all my processors, and inside you have a random forest that is also with n jobs -1 inside this loop. So this one is already using all processors, and then the random forests inside will also try to use all processors. So that will only create issues. So I would be careful only to use n jobs -1 for one thing, not multiple things that are nested. Okay, the last one here, it's a compact version. This is just using the cross-val score, which gives us less output. So this is using cross-val score, and here. So I would not recommend that unless you want to save some space. I think my notebook here crashed to run this again. Anyways, I would probably not recommend this one because it doesn't give that much information. For completeness, I will just upload this. You can't get the information about the hyperparameter settings though, which I think is a bummer. So it's a little bit shorter, more compact to write, but I wouldn't recommend that. Okay, so I don't want to keep you too long here. So again, the code examples will be on GitHub, so you can download them and play around with them. Next lecture, we will finish up all the model evaluation stuff, talking about evaluation metrics, for example, false positive, true positive rates, and we will talk about ROC curves, which hopefully won't take that long. And then I hope we can also cover some feature selection next week, but I can't promise. We have to see how we are doing on time. There's only one more thing I wanted to say, and that is happy Thanksgiving. I hope you have a nice break and you take maybe some break from studying and working, because it has been a really tough semester for all of us. I think we are all a little bit exhausted at this point, so it's good to take one day off at least and relax a little bit on Thursday. All right, then, happy Thanksgiving.